This
cover
conference will now be recorded.
he needs to get the ball rolling with the Amsterdam Summit. It's all yours, Brian.
Okay. Let's see. Share this. Okay. So, so I talked with the folks over there that are organizing the regional summit in Amsterdam in September, and they suggested we just fill out a spreadsheet that I put together that goes for what we're proposing as the half day. So I took the notes from last week's meeting in terms of who would be responsible for what. And basically we just need to put in here in terms of the timing, how long each session would be, and everyone's names, details, and then I threw in a spot for a co-speaker too. So, because I didn't think it would be a single person. In terms of the session description at the very bottom, that could be just essentially a 50-word abstract. I don't know if Poppy, if you have this on a shared drive for folks to be able to jump on, I think that would be good.
Yes, I will. I'll make a Google Sheets,
Okay.
and people can edit. I think it's fair to say we're open to other submissions too, right? This is the folks
This was
either
just the
volunteering.
concept. Yeah, this
Yeah.
was just the concept from last week. So if things have changed or if there's additions we want to make, then for sure, let's do it. Of course, this means that if you're signing yourself up, then you're also committing yourself to go to Amsterdam towards the end of September. This is due on May 24th, so in 2 weeks. So we need to have this filled out with all the proposed times too. Based upon just the 5 sessions already, I can see this as being a half day with which we had already agreed upon. So if once Poppy shares this, if people can start plugging away, I think it's a very simple process. We just need to just provide this to the organizers, and then we're done. Does that make sense for everyone? Okay.
If we have a lot of interest, what we can do is, assuming the OCP folks agree, is to split it into sort of a mini talks and longer talk session, depending on what the content is. So, if you'd like to volunteer, please step up. Don't assume this is the final list.
Awesome. I think that's all.
Okay. Then we've got Dave. I'll have you second. I see John Parks on, so we'll go with him first and you second. Is that okay with your schedule, Dave?
Yeah, that works just fine.
Thank you. John, thank you for joining. Thank you for presenting. Mark, thanks for setting it up. It's all yours.
All right, should we go ahead and get started then?
Yes, please. Michael, would you make John Park the presenter, please?
All right, let me know when you can see some slides here.
Sorry, we can see your screen. We can see something on your screen. I don't know whether.
You don't see the slides?
We don't see the slides.
Nice white box.
We see a calendar reminder, ODSA WebEx in 5 minutes.
Okay.
Yeah, we see your calendar reminders.
All right.
You should see an option to share either your full screen or just a single application. You may want to look at that and make sure you're doing the right thing. And Rajesh, we're getting a ton of static. Do you mind going on mute? Thank you.
All right, how about now?
Yep.
Okay. Can you see, is it in full screen mode for you?
No, we saw the slides when they weren't in full screen mode.
And now they went away. Okay, interesting.
Yeah, now we can see them, but when you go to full screen, they're gone.
So when I go to slide mode, all right, I think we're gonna have to try this then without, if it's okay with you, it doesn't look like I can go into slide mode, so it should be fine.
That's fine.
Is the screen big enough for everybody? I'm not sure that I can make it bigger, but all right, okay. So thanks for inviting me. My name is John Park. I work for Cadence Design Systems, where I have product management responsibilities for our advanced packaging and what we call cross-platform solutions. And cross-platform meaning solutions that tie together the chip, the package, and the board domains. And the title of my talk today is really to focus on some of the new. I think I'll start off with kind of our definition of multi-chiplet heterogeneous integration, more than more, whatever term you want to assign to it, kind of our definition of what that all means and how it's impacting the tools that we create, and then go into a couple examples. So the outline is exactly that, a couple slides talking about how we look at the market of multi-chiplet design. And then kind of, due to the limited amount of time we have here, we don't have enough time to go into too much detail. So kind of from a high level, talking about some of the flows and solutions that we either have historically had, or as well as some of the newer technologies. And I'll kind of go into one of those flows at the end of my talk. All right, so a couple slides here talking about, how we view this kind of more than more multi-chiplet heterogeneous integration sort of trend. From my background's in microelectronics and specifically semiconductor packaging. So from that perspective, looking at, and choosing this term heterogeneous integration, which a lot of people are throwing around now, it's nothing new to us in the packaging world. We've been doing multi-chip modules using different exotic non-silicon materials and integrating those together at the bare die level for several decades now. So from that perspective, we've been involved with this sort of heterogeneous integration from a packaging perspective for a long time. So that's kind of the long ago past. Not that doesn't continue, because it does, but we've kind of accelerated this approach to multi-chip and multi-chiplet design over the last decade or so. And I'm going to talk about that in a couple of slides of why we think that is, but we've kind of migrated to these, the example kind of there in the middle at what the industry calls a 2.5D integration, where to reduce the latency from the processor to the memory, which was traditionally placed on the board, taking the memory, stacking it three-dimensionally, and then moving that next much closer to the processor, typically on a passive silicon substrate, where the interconnect is then added. So that's in some people's definition, that is heterogeneous integration, which it is. But kind of way we look at it is kind of the extreme approach all the way on the far right, where I call the disaggregation of the SoC, where instead of me designing a huge SoC at 7 nanometers and getting IP that all has to match 7 nanometers and going through the expense of all that and the resources that are needed to do that, basically taking a different approach where you are still using IP blocks, but you're not concerned with the process node or the technology that IP was created on, and then reaggregating all of that IP and your special sauce onto either a silicon interposer or some sort of carrier, and it's kind of then so you tearing down the SoC and then rebuilding it in almost like a small PCB approach. So what this all means from an EDA perspective is the types of design tools that people need to do these types of designs. The design on the far left, the multi-chip module, those were PCB style, schematic driven sort of approaches. And as we move to the far right, that becomes more of a traditional IC-like design flow where you have additional requirements for the sign-off part of the flow. So closing on timing, doing your final LBS and DRC, probably not schematic driven, so on and so forth. So it's kind of an evolution of change for the EDA tools. So that's kind of on the what I call the logical partitioning side of things. We also have at the same time these changes going on in what's available to and how we package things. So historically, it wasn't that long ago, 30 years ago or so, where everything was a lead frame. We had a huge transition when the ball grid array came out in 1989, 1990 to a completely different user base and a different set of tools. Cadence created some tools back in the early 90s for this new approach to packaging, and so we're familiar with this sort of paradigm change. And now we're in this mode where, because of TSVs and fan-out wafer level packaging technology, we are seeing another sort of big paradigm change in the types of the expertise required to put these things together and the design tools and design flows. Again, migrating from long ago mechanical tools to PCB-like tools, and now moving to design tools and expertise that exists in the semiconductor design world. So those are kind of the two big changes, along with a third I'll mention here. So what more than more means to us is a combination of primarily three factors. And I'll categorize those as logical partitioning changes, when that's the multi-chiplet approach that we'll talk more about. We see kind of physical packaging technology evolution that's impacting that, as I said, through silicon vias, and fan-out wafer level packaging means that there's more silicon content essentially inside of these packages, which changes the types of design tools that people need. And then the third factor is the fact that the semiconductor foundries are now offering their flavors of advanced packaging. So we have kind of an ecosystem change going on at the same time. So there's logical partitioning in this chiplet-based approach, the packaging advancements, and then the foundry change, or the ecosystem changes as the foundries get into this. The foundries getting into advanced packaging, from my perspective, is a great thing, because they bring with them the idea that you don't just say, hey, I've got a new technology, and let people guess what that is. They actually get involved with creating reference flows. So if you're going to start a new design, historically package designers there was no concept of a reference flow or a PDK. That's now starting to change as semiconductor foundries are joining the game here and providing such a data. So this is also driving the OSATs, the outsourced semiconductor assembly and test companies, to join the bandwagon and start to develop reference flows. So from a end user perspective, that's a positive trend that's happening in the industry right now. So kind of a brief introduction. I'll finish with some of the challenges of this new multi-chiplet approach, and we'll talk about some of the solutions that we've created for this. So, whether it's multi-chiplet approach, really the driving factor in most cases is the type of packaging you're going to use for that, whether you're going to put them on a silicon interposer, whether you're going to use a fan-out wafer level process, whether you're going to use a thin film laminate. Those types of factors play an important role in the types of design tools that you typically will need. I've listed here some of the challenges or the specific features that people look to as they go to these multi-chiplet approaches. I'll highlight a couple of them. The second bullet there, the right level of abstraction in the layout. So if it depends whether it's a chip or chiplet approach to how you do the planning and layout. In a traditional multi-chip approach, the level of abstraction is pretty high. It's typically the extents of the die and the locations of the pads and maybe the signal name associated with that pad. And because the end goal is the assumption is made that the timing closure and everything's kind of been signed off out to the edge of the chip, and your job as a system integrator is just to correctly connect those multiple chips together. So you can work at a high level of abstraction. If you start going into true chiplet level design, where you have to do there are some additional requirements on exactly what level of abstraction you drill down into that chiplet. And if you're doing something like timing closure, you've got to go down, down to basically the transistor level. So you have to have a more kind of a more complete representation of the chiplet in that case as you're assembling the system. So that's one factor. How people define connectivity is often overlooked, but important in these flows. If you're an ASIC designer, you typically capture everything in an HDL and have synthesis tools and that sort of approach. If you're an analog designer, typically it's a schematic-driven flow. Package designers use spreadsheets. So it becomes this aggregation of all these different needs as you get into a multi-chiplet approach. So you have to look at a pretty flexible connectivity model where you have a platform that supports various different modes of capturing the connectivity, and I'll talk a little bit more about that. As you move into these packages with more silicon content, and we've talked about the IC or semiconductor sign-off tools start to play an important role because you're creating mask sets instead of Gerber data. So additional requirements come in there as far as sign off for LVS and DRC and metal fill and those types of things. Electrical modeling across the complete system, it's potentially a much bigger three-dimensional problem. So you have to reevaluate the types of tools you're using for the electrical modeling characterization on the back end. And then a very important thing to consider is, if you're mixing multiple chips or multiple chiplets, you're essentially mixing together multiple PDKs. And historically, when you netlist out to your simulator to do your functional simulation, if you're going across different PDKs, you have what we call namespace collisions or conflicts, where you have the same model name, but it's in two different process nodes or in two different technologies. So you have to make sure your netlisters are able to handle multi-PDK types of designs. So those are some of the challenges and kind of an overview of where we're coming from an EDA tool provider perspective. Let me talk a little bit now about kind of some of the tools that we have either built or building right now, or have improved the capabilities within those tools. So from a high level, at Cadence, we have an initiative from our CEO that started about 4 years ago now, when he and like a lot of us kind of saw this kind of a change in the market where things are more system oriented. Cadence, who was mostly a tool provider for designing chips, we do have package and board tools, but from the CEO level, we were asked to look outside the chip and look at system level implications to these new types of approaches. So this is not one little group at Cadence that's focused on this. The whole company is taking this kind of approach of thinking bigger than the chip and looking at the rest of the system as we put it together. So because of that, we've created these new cross-platform solutions, number one, and number two, Cadence, who historically had a couple of point tools for package design. For multi-chip design, there we had a tool. We still have a tool called SIP layout, a tool called APD, and then we had some electrical modeling tools. That was the past. The present is now since we're taking this kind of holistic system level approach, is we've extended the capabilities of all of our implementation platforms. So they know how to work with multiple PDKs, with multiple representations of chips and chiplets. That extends from the planning tools to the implementation tools, and all the way back into the back-end sign-off tools. So they're all what I would call multi-chiplet aware, which is a big change. The database changes so that IC layout tools understand what a through silicon via is, what backside metal is, what a microbump is, how to handle multi-dies in general. But one of the big changes is we work with a lot of customers, obviously doing this type of design, and there was no kind of central entry point for planning and, most importantly, managing this system level type of design. So we have some technology we call Orbit.io, which is kind of the single entry point, regardless of what tool you're using for implementation and sign off. We have a central entry point that works with chips and packages and interposers and boards in a single canvas, and allows you to kind of plan out, pathfind your overall solution, whether it's multi-chiplet, multi-chip, whether it's fan in, fan out, all the different possibilities. Allows you to work in this sort of sandbox mode. That's one part of what Orbit.io does. The second part is it provides the data to drive the sign-off tools in the back end. So typically you do your upfront planning, and you might use a couple different platforms to do, one tool to do the ball grid array that it's going on, a different tool to do the top level chiplet integration. And at the end of the day, you need to reassemble all that and validate it at the system level. So this Orbit.io tool is the tool that provides the most importantly, the golden net list, so that at the system level, you can have the confidence to tape out your design knowing that everything is connected correctly. It contains all the information of the orientations as well, so you know how things are stacked and rotated and all that. So it drives, it's a planning tool, it's not an implementation tool, but it drives into the implementation tools, and then it drives, if you look at the arrows on the side, into the sign-off tools to kind of re-aggregate the system when you're ready to tape out the design. So this is kind of the high-level view of these, what we call cross-platform flows, where we started to integrate the different domains, chip, package, and board. A little bit more specifically about the implementation platforms themselves. We have at Cadence 3 primary implementation platforms: the Allegro technologies, which were our ball grid array and PCB design tools and still are. Virtuoso is our analog and full custom platform, and then Innovis is our digital SoC platform. So as I mentioned earlier, all three of those platforms now are chiplet aware or multi-chip aware. They understand and know how to represent and model things that involve multiple PDKs and multiple chips. The databases all are also aware of what a through silicon via is, what backside metal is, or what we call chip tiering, how things are stacked and how they're oriented. So yes, there's a lot of redundancy there, and that redundancy is on purpose because there are advantages and disadvantages that come along with each of these platforms because they were architected for different use models. On the Allegro technologies, that class of designer is more accustomed to handcrafting and more interactive editing type of approach, and the same would apply to the full custom Virtuoso, where it's more human interaction. And then as you get to the digital solution, it's more about you're dealing with billions of instances potentially, and so it becomes more of a batch type of environment. So there are different use models here, and different advantages and disadvantages to these. But again, they have a single entry point. and they also all can drive into the LVS and DRC tools, all of them at the back end. So one of the things that, a couple important points here is capacity typically plays a pretty big role here. So if you're doing something that's RF analog in nature and you don't, you're dealing with hundreds of thousands of instances and want to do more artwork, more hand tuning and that type of work, that would be a big important factor for which platform you choose. If you're doing something that's, dealing more with, we've got one customer that has hundreds of millions of hybrid bond pads between their stacks. So as you get into hundreds of millions of instances, that kind of throws out the Allegro platform, and you have to take a look at one of the semiconductor platforms. So capacity is an important factor when you choose one of these platforms. The second point I'll make here is that our customers today often will use a couple of the platforms because of the advantages that they want to take advantages of one of the other platforms for, say, its routing abilities. Because of that, that's the other big initiative at Cadence is we've created, as part of these cross-platform solutions, that we've created much tighter integration kind of horizontally between these platforms. So using open access, using another flow I'm going to talk about in a few seconds, we've made it easier for our users to start a design in one platform, go off to another platform to take advantage of some particular advanced feature it has, and then come back into that platform to do the tape out. So that's a pretty big change at Cadence. I'm going to give you now an example of a flow we announced last year that was specifically architected as a multi-chip and a multi-chiplet flow. We call it Virtuoso System Design Platform. The name's not that important, but what it is, you can see from this high-level diagram, is it's in the red there, is it's a bidirectional bridge between our Virtuoso tools, which again are analog and full custom IC design tools. So it's an integration of that platform, the schematic capture, the layout, the circuit simulation. All of that gets integrated into our Allegro-based technologies for package and board design. So it bidirectionally drives the net list and constraints into the system level tools, where then they start to be implemented. And the second part of the flow is it allows you to extract the layout parasitics of that ball grid array or the reference board and seamlessly feed those layout parasitics back into the Virtuoso platform, so that you can do your final sign-off simulations and look at performance with all the impact of all of the downstream layout parasitics. A little bit more about that. It's really the name's not that important. It's really about this system design enablement, intelligent system design, extending beyond the chip and looking at a system level implementation. So again, it's a platform that integrates three of our big platforms, Virtuoso and Allegro, our implementation platforms, and then it brings in Sigrity, which is our electrical modeling, 3D EM. It does power analysis and signal integrity checks as well. And so we believe, from what our customers tell us, it's the first, formal multi-chiplet solution. People have historically hand-stitched things together. This is a formal, fully supported solution for multi-chips. It includes one very important feature, and that's layout versus schematic checking. When you assemble the whole thing, again, you need that top-level golden net list to validate that the multiple chiplets are connected correctly, or the multi-chips are connected correctly. It's another powerful feature is what we call edit in concert. So it allows you to concurrently edit the substrate that these multi-chips or multiple chiplets are sitting on at the same time as you're editing the chips or chiplets. So from a single view, it is two different tabs, but from a single platform, you can kind of switch between the tabs and kind of, while you're looking at the complete system though, switch between the tabs and do specific editing across the different implementation domains. And of course, as I mentioned, it links in our the 3D EM technology, so it allows you to model and create much more advanced models of electrical models of the types of layouts that you're going to see as you move into the system level integration. It integrates also in our Allegro-based technologies. I'll touch on those in a second. That historically, I think maybe the start of the whole genesis for this meeting was someone found a spec sheet on a product that we call SIP Layout. This product's been out for over a decade now. It's kind of the industry standard, de facto standard for multi-chip integration. It's used by all the OSATs. It's it's a very flexible environment, everything from a single chip wire bonded PBGA all the way to fan out wafer level packaging to silicon interposers and everything in between. A couple of unique things about this platform is it does allow the manufacturing output of semiconductor processing equipment, so it'll output GDS, and it will also output board level manufacturing data like Gerber and IPC 2581 and those types of formats. So it is truly it's substrate agnostic. We don't care whether the substrate's glass or silicon or ceramic or thin film laminate. It handles all of those types of substrates pretty well. And again, it's got a flexible environment, flip chip attach, wire bond attach, all the different methods for attaching chips or chiplets. So the combination of those tools, we don't have enough time today to go into the gory details, but this is what the multi-chiplet flow diagram looks like. It starts from the bottom and works its way up. So this example is a 3-chip integration. What this new platform does is it creates levels of kind of a hierarchical representation, in this case of the 3 chips, both a logical representation as well as a physical representation, and that allows you to use that level of hierarchy to capture your top level system design or schematic, as you see in the top middle there, and then a bi-directional interface to drive the implementation tools, to do co-design, to net list out across multiple PDKs into the circuit simulation environment. And then finally, of course, the ability to point to that system level layout, whether it's a module or a package or a board or all of the above, in combination with vendor provided device models, and do a 3D EM extraction on that and feed that layout parasitic model back up into the top level design where you can do your final system level sign off. So in summary, we don't have a lot of time to get into too much detail here, but in summary, is what Cadence has done to kind of address the needs of these multi-chip system level approaches, chiplet-based approaches, is we've kind of made pretty substantial changes to our implementation platform so they understand these new ways of logically partitioning and physically, and the new physical capabilities of stacking and so forth. We've extended that capability all the way to our test tools and all of our sign-off backend tools. So RC extraction, DRC, LVS, timing closure, all of those tools have been enabled for multi-chip and multi-chiplet design. And then finally, we don't do all this in a cave. We do work with a number of partners, both IC foundries, OSATs, as well as system customers. And so we've done a number of tape outs of these multi-chip, multi-chiplet types of designs. We have reference flows with OSATs and with the semiconductor foundries. And so in short, we've kind of, well, that concludes my talk. Again, looking at the whole big picture from an EDA design tool perspective. Any questions?
It seemed like you quickly slid by the most important point there on slide 16. You know, your tool makes it sound like the goal is to enable everybody to design complete platforms from the transistor up to the top level. But what we're really after is that non-native IC integration, so not everybody has to go down to the transistor level.
Correct.
The question is, how do you make it easy and straightforward to work with those non-native IC layouts?
So we have lots of different, so you're exactly good observation there. So not every chip is going to be done inside of a Cadence tool. It's going to come from somewhere else. So we've made it easy to bring in, multiple views of that chip layout. So in some cases, all you have is a simple abstract that says, okay, the chiplet, looks physically like this. We can work at that basic level of just using parameterized data that says, okay, the size of the chiplet is this. These are the sizes of the microbumps that attach it, and these are the signals that connect to that. We have multiple views, so if they also have a behavior level view of that model, that gets associated with that particular chiplet, so that you can include it when you're doing your simulation runs.
But even if that chiplet does come from someone who's using a Cadence tool, they may not want to provide ultimate visibility down to the lower levels. So do you make it straightforward for them to export specific and appropriate views?
Yeah, so if it's coming from a Cadence tool, we support multiple levels of everything from the transistor level up to what we call an XDA file, which is a high level die abstract file. So the user, picks and chooses. Typically our customers, if it's all coming from the same company, they typically want to provide as much detail as they can, but that's up to each individual company. Like I said, you can go all the way to the transistor level. You can have just a behavior level model. You can have no model. There's various different, when people do multi-chip approaches, it's typically just an I/O model. So it'll be a black box representation of that chip, and then they'll provide the kind of IV and VT curve, the switching behavior of those I/O. And we take that as well. IVIS is one example, one format for doing that. So that when, if you want to treat the chiplet or chip as a black box, but still look at the behavior of, the signal as it is sent and received from that chip, that's all supported within the flow as well.
Thanks, John. That was actually, I'm hoping you'll come back. I'm reasonably sure once we understand what these slides in more detail, we'd love a follow-up if you're able to do it.
Yeah. No, we're limited to a half hour here, so there's a lot to talk about in a half hour. And if there's any, one specific area that you want to, take a closer look at, I'm happy to come back.
Yeah, thank you. No, we had two exciting topics, and I needed to get both of them on the agenda leading up to a June workshop. Thanks, Mark. If you have follow-up questions, I think John's definitely open to coming back, and I'm going to follow up with him offline. Okay, thank you, John.
You're welcome.
Our next speaker is Dave Kellett. He's everything AIB at Intel. So Dave, the screen is yours.
Great. I'm going to share my screen here.
Yeah, thanks. Yeah.
Okay, you folks see anything yet?
We see both windows, both the slides and the GoToMeeting window.
Okay, how about that?
Yeah, much better.
I'm going to leave it in edit mode here, given John's experience. I think you can still see the slides. What I wanted to talk about today was not really the PHY at all, but it's kind of the next level of interoperability on what are the protocols that you would want to run, given that you have a die-to-die PHY. And we approach this taking a look at the use cases. And rather than having a protocol and mapping the use cases onto it, it was the other way around, which was what are the use cases that you need, and then what are the protocol or protocols that are required in order to serve these use cases. And some of the use cases that we came up with and that we actually have at Intel, and it's probably come with other folks, we have really the top one is one of the primary use cases we have. We have a streaming protocol, and this is some network data coming in, and it could come in from a SerDes, could it come from a Mac? Ethernet is huge, so this falls right in this camp here. And there's another very similar one in use case characteristics, which is live sensor data. So if you have an RF ADC, something that's just generating tons of sensor data, this is another that falls in the streaming protocol use case. Then there are a set of transactional protocol cases, which in some, like control and status registers, it tends to serve the first case, meaning you've got a device out there, a chiplet, and you need to configure it. Maybe it's set up PLL parameters, sample rates, and what frequency you're running at. So that would be a controlled status. There's another one is chiplets are getting to where many of them have embedded microprocessors on them. All these advanced devices now for calibration, lots of people have gone towards the microprocessor approach there. So you need to load firmware, do configuration of the devices. And of course, there's a memory case. Some folks have been thinking about, could I take a new memory controller and stick it on a chiplet and decouple that from the development of a giant SoC that you could more quickly enable that SoC with a new memory type. And then finally, one of these that I'm thinking, given that the name of this organization is probably particularly interesting, is the accelerated use cases. And one of them that's different in a lot of respects than the above use cases is if you need this coherent view of memory. And it could be device attached memory, it could be host attached memory. Either the host or the device may need to access it. So this is not necessarily a comprehensive list of use cases, but these are ones that kind of have been in the forefront of us thinking about what sort of ways do we need to serve heterogeneous systems that we're interested in. So I'm going to go through a few of these cases here. On the streaming protocols, we found really a simple protocol works really well. If folks are familiar with AxiStream, it's very simple. I got this little diagram in blue on the right here. You forward a clock, you forward your data, you can send a valid signal across, and the downstream partner can send a ready for flow control. And the AxiStream spec is really great at how it specifies this, that it doesn't say that data valid and flow control are optional, which is kind of difficult for a standard. It says, here's what you do if the downstream partner does or doesn't support these. Now, what we found is that things that are built for ASIC module-to-module protocols often don't work well die-to-die. The PHY is generally going to introduce a few things that you don't have on chip with a common clock domain. You have things of like clock phase differences between the upstream and downstream device. You have channelization, so now you have clock phase differences between channels, and you are likely to have pipeline delays if you're running at a high performance level. So what we found is that you may need to modify one of these protocols that was really built for on-die module-to-module interfaces to allow for phase delays and pipeline delays. And that said, your life becomes a lot simpler if you don't actually have to implement a ready style flow control, which, as I noted above, the AxiStreaming allows for the downstream partner to not support ready. And the use case we like really very much is when you're running your interface at really the line rate divided by a factor. If it were 56 gigabit Ethernet, that you divide this down to some level to where your die-to-die interface is really that 56 gig line rate divided by n. And the reason we like this is then you're running the interface at its absolute lowest rate, so you have the lowest power. You don't need asynchronous FIFOs. and some really obscure requirements that apply to certain wireless applications, such as deterministic latency, that you don't have to go through FIFOs and deal with some uncertainty there. So if you, on the channel, the picture on the right, if you get rid of this ready, then it's just the data goes across, your valid is paired up with the data in the clock, and the complexity of crossing a die becomes much simpler. Now it does mean that your flow control gets pushed further downstream, so somewhere along the line, this goes through a MAC, it goes through some application and has to decouple from the line rate into some other system clock. Now, paired up with the streaming
Dave?
protocols is, yeah.
On the previous slide, so if you wouldn't, sort of a numerical example is, let's say if the streaming slave is the network interface and it's 56 gig, then you're...
Yeah, go ahead.
I was going to say, would you mind giving a numerical example of this multiple, the idea of the multiple that you're talking about? That, say, if the streaming slave is the network interface at 56 gig, then this yellow block would be at 28 gig or something like that?
Let's suppose you're running a 25 gig Ethernet, and so the line rate there is like 25.875, something like that. You basically just, let's suppose we're going to run this across at 2 gigabits per second. You divide this down by a factor of 12 or so from the line rate. Let's suppose that the network interface were the master, so you have data coming into your SoC on the right. So where I'm not showing anything on the left side of the master here, you could have the Ethernet data coming in, then it gets divided down, deserialized from 25 gig down to 2 gigabits per second across the N number of wires now, and then sent across to the SoC on the right. Does that make sense?
Yeah, it does. Thanks.
Yeah, it would have been helpful if I'd actually worked out the actual numbers on that. That's a good idea. We inevitably have a need for a transactional protocol, and in some cases you want to do this across a die-to-die interface because you want really fast control status register updates. If you don't care about the speed of this, then use SPI or use something else. But there are situations where we want to do a really fast reprogramming of the other side, and so using a high-performance interface is appropriate. And there are existing on-die module-to-module interfaces. One's been around a while, the AMBA APB. And it's very simple. The master sends a request and the slave responds. And you end up with something that could look like the word formats I'm showing on the right side here. You have a read and a read response, or a write and a write response. You have a word count in here. And there's a variety of flow control schemes that you could use on this. You could use a non-posted write. And non-posted write, I always remember, non-posted is longer than posted, just number of letters. And that means non-posted is the one where you get the right response. So you do a write, and then you get a write response or acknowledge that the write is completed as a way of throttling your issuing of writes to match what the downstream partner can do. Most of the protocols have now use a credit scheme for better throughput and utilization. It's a little more complicated, but if you really do care about high performance, you'll see that pretty much everybody's using a credit scheme now. And a credit scheme is the downstream partner says, I can accept N more transactions, and so they will issue credits to the upstream person to enable the upstream partner to be able to issue reads or writes to the downstream partner. PCI Express is probably the predominant chip-to-chip, or maybe even die-to-die. We have some Intel products that do this protocol. Now, the upside for PCI Express is there's a gigantic framework of software for it. And PCI Express is is been worked out over a very long period of time, very high performance, reliable transfer, different classes, very sophisticated. Now that sophistication is also a downside. You can end up with a complexity mismatch with what you're trying to do on the chiplet. So let's suppose your IO chiplet here is a 25 gig SerDes. And just to talk to that SerDes now, you're going to go through a PCI Express endpoint that doesn't really make sense. So you kind of have to match the protocol with what you're trying to do. Given that you have to, if you're going to implement PCI Express, you have to put a controller on the chiplet silicon. That's that on the right side, that PCI Express endpoint controller. It has its own size and power requirements. You're going to spend some latency getting through that controller, and depending on your application, if you don't care about latency, and there are plenty of applications that don't. If you're doing some long haul optical, latency may not be as important as if you're doing some real-time control, electronic warfare kind of application. And finally, here's one that doesn't get thought about a lot yet. But when we've talked to a lot of folks on this DARPA CHIPS program, they're saying, hey, look, we're going to build 10,000 of something, and we can't afford to spend $1 million, and that's being generous. I don't think you can buy a Synopsys controller for $1 million. They can't burden their part with a $100 cost just for the IP licensing. So that's something to think about as well. And that's one of the barriers that I've been looking at as far as die-to-die interfaces is how do you reduce a barrier of IP availability. Okay, so that's PCI Express. Now we get to the accelerator use cases. Boppy, thanks for suggesting I take a look at CXS. So I have an example. CXS is this protocol to connect up CCIX along with to a PCI Express controller. It's a streaming interface, not all that different from the AXI streaming case that I mentioned earlier. It doesn't have writes and reads. You have a CXS interface going one direction, and you have another CXS interface going the other direction. Now, to implement this on top of PCI Express, depending on what the controller's native interface to the application is, because we're talking not the line side of PCI Express, we're talking the application side of PCI Express. So depending on what that interface looks like, you may need a shim on top of that to implement CXS that should read. It's not that big of a deal because CXS is pretty simple. I just zoomed in on the thing out of the spec here at the bottom here. You've got the data, valid and some control that go in each direction that you have a CXS interface. The content of the data is up to the modules on the either side, so it doesn't have a packet format. You think back to this one here of an APB. Somehow in here you have to put am I a read? Am I a write? There has to be some header to tell you what the request is. With let me get back here to CXS. It doesn't care about the content. That's not its problem. It grabs these flits from one side and sends them over to the other side. I mentioned that credit-based flow control. So this is a modern protocol. This is kind of the way most folks have done this, including PCI Express, to have a high utilization and high bandwidth. I want to say, yeah.
So so there were two questions we were sort of poking around on. One was whether CXS could be like an AMBA, just a simple link layer protocol all on its own. And the second was whether you could move CXS directly over the PCI PHY, bypassing the PCI MAC layer. Then because you still have the same high dollar cost problem when you're trying to move it over a PCI.
I think the answer to the first one is yes, that it is a simple, you stream data from one side to the other. There's no wiring level flow control on it. To the second one, I'll talk to this in a minute about pipe. As you can see in the diagram here, they envisioned that this thing's actually talking to a data link layer,
Right.
and that would exercise the the reliable transport between the two sides. But in the realm of a simple streaming interface, so it's somebody else's job to deal with reliable transport. So I'd have to say I believe that is possible because, and I want to talk about pipe. So I'm kind of working my way up to that. If you just give me just a second here. Sometime since the last workshop, Intel announced CXL, and if you dive into the CXL spec here, you'll see the PHY interface is what it the Compute Express organization is called FlexBus, and you can see it's still very SerDes oriented, meaning that they're thinking ahead to I'm going to have 32 gig SerDes, 16 of them, for a 512 gigabit per second interface, and you're allowed to do, instead of by 16, you can do by 8, by 4, and so on. This is also this FlexBus interface here is also a streaming interface. They have intended all along that you're going to be able to carry different protocols across FlexBus. So it has a protocol ID. It's got a 528-bit FLIT. It's got a null FLIT. So this is basically data not valid. And the credits are handled by somebody else up in the link layer. So at the PHY layer, you don't have to worry about the credits. So the question I was thinking of is there a pipe interface inside the FlexBus PHY? Well, it doesn't tell you that there is. The spec doesn't answer that point. So you're kind of left when you read the spec of, gee, where's the porting layer? If I want to put this on top of my PHY, where's the porting layer I have to provide if I wanted to run CXL on top of this? You could do it the FlexBus layer, great, but you would almost prefer, hey, somebody else, maybe the CXL organization, ought to provide the FlexBus shim, so that I can do something that's a little more looks more like a PHY itself, closer to the native PHY down at the lower end. So that's still a question I have: is there a pipe interface inside this? Highly suspect that there is, but it's not in the CXL spec identified as a layer. Okay, so I think that the discussion about pipe is going to come up here right at the end. So my conclusion out of this is one protocol is not going to meet all these use cases, and there are a lot of people. Their highest order bid is I need to match my use case, and I need it to give me exactly what I want. I can't use an existing board level interface, something like PCI Express. So I'm thinking there might be two camps of folks, and the first are those folks who really, if they didn't have to do heterogeneous integration, they would do it all monolithically, and so therefore they want really something that's equivalent to a module-to-module protocol, and that would be the AXI style protocols. And I think maybe there are even more camps, but there's another camp that's really this large-scale integration. People are doing these accelerators on PCI Express boards right now. These are the folks that are interested in C6, OpenCAPI, and CXL. All right, so now we kind of come to the heart of this thing here, which is, how do we find a common denominator? If you wanted to achieve some kind of standardization, you want some sort of, a standard interface. I think the folks that use these AXI style protocols, they like their lightweight protocols. They are not going to let go of them for reasons of latency, size, cost, and so on. Now, you get to CXL and C6. These things have been built to layer on top of PCI Express pipe, and I'm speculating a little bit on CXL, but I think with good reason. OpenCAPI, the original CAPI was on top of PCI Express. OpenCAPI has gone to really getting rid of a PCI Express controller and just doing it native. TileLink is yet another one that is not PCI Express pipe oriented. So Boppy, back to your question now. Could you do CXS on top of PCI Express pipe? I believe the answer is yes. I think the data path, it's really straightforward, that you wouldn't really have to add anything in the way of the data path, meaning no extra registers or muxing or anything like that. You might have to do a width conversion, and I know you were working on, what is the width there. On the control and the other related signals of this, you may have to do some things because pipe is assuming a SerDes is there along with a handshake for coming out of reset and achieving calibration, that you probably would have to do some kind of shim there, but we'd already anticipated that if you want to implement something on pipe, you would stick in some dummy state machines. If you didn't really have a SerDes underneath it, you would have some dummy state machines for those and probably have some logic to bring up whatever kind of PHY that you actually have. So that's kind of where we're at here. I think we are going to have these two cases. I think being an accelerator organization, this group is probably more interested in these things that people are building as PCI Express boards right now, as far as true accelerator interfaces, things that offer the coherent shared memory.
Well, we're envisioning what you have on the bottom bullet, the CXL or C6, or riding on top of an AXI style protocol that is the actual chip-to-chip link protocol, either AXI or CXS. That there is a light link layer between chips, but on top of that, there is a coherence protocol that rides on top of them. That's the basic thinking in flight right now.
Yeah. So I think that's kind of a little bit like this. We're just trying to decide where does the arrow actually point.
Right. That there will be in room for an AXI protocol, no matter what, and then you decide whether on top of that you want to run the coherence or not, or CXS, AXI, CXS. I think the difference between AXI and CXS seems to be the amount of control. AXI seems to actually want to control the peripheral too.
Well, if you're looking at AXI streaming, this is it. I mean, it's actually very simple.
I see.
AXI streaming. If you're looking at AXI memory map, which is transactional, there are 5 different buses, so that's much more sophisticated and complex.
Sorry, any questions for Dave? I've sort of been monopolizing their time. I apologize. Actually, I'm hoping Quinn might have something for you, but I think he's at some location right now.
I'm at the CXL workshop.
Yeah. So
great. Well, why don't you ask him that question? Hey, is there a pipe interface inside FlexBus?
Yes, because FlexBus is just PCIe PHY layer.
Well, no, it's actually more than that, because it defines a streaming interface of protocol ID and FLIT at that layer of FlexBus. So it's a little more than the pipe.
Because it provides partitionability, but fundamentally, you can abstract it to that.
Any other questions for Dave? Mark, I'm assuming you'll have like a couple of PCI guys that we can actually link up with Dave sometime over May and June.
Yeah, actually, a couple of folks from our PCI team agreed to join in and participate. I think Paul's on the phone, and we'll definitely want to set up some time to get everybody together.
Perfect.
Good. Yeah, I'd welcome that.
So Dave, as you know, I think we've put some effort into the PHY layer. Now we're sort of migrating upwards to the link layer and above that. So this is a great kickoff talk for us, and I'm hoping we can engage.
Good. Yeah, I think so.
Okay. In that case, John, Dave, thank you. Both really engaging talks. If there are no questions, I think it's too late to do open. So Dave and John, could you please send us your presentations? We'll host them on the wiki.
Sure.
And Dave,
Sure.
I know you said you're busy in the middle of May, but at some point we are going to kick off this die to die stuff, and I'm gathering volunteers for the effort.
For the die-to-die link layer?
Exactly, the die to die link layer.
Okay. Sure.
And John, I'm reasonably sure we're going to have follow-up questions for you for our base for the prototype we're building. So I'll circle back with you sometime this week.
Sounds good. Thanks.
Any opens from anyone online? Going once. All right, sold. Thanks all. Have a good weekend.
Thank you.
Bye-bye.
Thanks.